Okay, so what we're going to take a look at today is Rutherford's alpha scattering experiment and how it provided evidence for the nuclear model of the atom. So let's start off with how we knew there were atoms to start with before we start plumbing the atomic structure. So they've known for a long time that essentially matter could be broken down into small chunks, and they called them atoms after the Greek atomos, which means indivisible. But one of the first things to actually really see atoms existing was an experiment called the Brownian motion experiment. So what you've got here is they put dust particles or smoke particles into a gas, and what you can see is the dust particle here, or the smoke particle, is constantly changing direction. So you can see it's been colliding with lots of smaller different particles behaving in an entirely random way. So the path of this dust particle is different every time you put it in, or if you watch it you'll never see the same pattern twice. So it shows us that gas particles essentially behave randomly, and that there are these individual atoms or molecules which are colliding with it. So it's the first time we actually really saw the atoms in action. They knew before, but it's when we saw it. So that's how we knew there were atoms in the first place, and we've got a nice little animation I found online there. So if we look onto what evidence we found for the nucleus, so this experiment was supervised by Rutherford, but it was actually carried out by his two students, Geiger and Marsden, who you might have heard of as well. So they knew that atoms were made up of some parts positive, some parts negative, because J.J. Thomson has already come along and he's already discovered the electron. So we know there are negatively charged parts of an atom. We know an atom is neutral, so therefore there must be positive parts. But what we don't know is where that positive charge is. So what we did is created this experiment here. We fired positively charged alpha particles out this tiny hole here. So there was a fine beam of alpha particles. And what it does is it collides with, or essentially tries to collide with, this gold foil here. And you've got fluorescent screen all the way around to detect where the alpha particles actually end up as a result of their collisions or not collisions with the nuclei of the gold. So that's the general setup. So what they saw was a few different things. So looking at their their fluorescent screen, what they saw is most particles here were either deflected by a small amount or were actually passing through undeflected at all. So that's one of the observations they made. But they noticed a few of the alpha particles, very few, something like 1 in 10,000, were being deflected by more than 90 degrees. So what they did is they came in, this would be deflection of 90 degrees coming down here, so you can see this one is deflected by more than 90 degrees, and some are even deflected by 180, so bounced straight back. So those are the two observations that they made. So what do those observations actually tell them? Well, the fact that very few particles are significantly deflected tells you actually the nucleus is very, very small, because only a few are actually significantly deflected, so have come close to the region of positive charge. And it tells you that the positive charge is concentrated in a very small area. So to be able to turn around an alpha particle requires quite a strong positive force to repel it, so that must be concentrated so you have a large positive charge. The fact that most pass through the gold completely unaffected or minimally affected tells you most of the atom is actually empty space. So before they had this idea it was kind of an atom was built of solid parts, but actually what this said was actually most of it's just empty space. The area we now know is occupied by the electron clouds around the nucleus. Okay, so let's take a look at some of the assumptions behind the alpha scattering method. So one of the assumptions you need in order to draw the conclusions that they did was to assume that each alpha particle will only interact with one nucleus. Okay, so what that means is that each alpha particle hasn't interacted with multiple nuclei, which is called multiple scattering. So we've got single scattering going on. And the reason it's a valid assumption to make for this experiment is because gold foil can be stretched extremely thin because it's so ductile, and because of that it can end up being only a few atoms thick for this experiment, so it's incredibly unlikely an alpha particle will encounter multiple nuclei. So that's what's going on there. The other thing involved in this is they were assuming the alpha particles would only interact with the nuclei through the electromagnetic force, so the force between charged particles. But as we know, that's actually not a valid assumption once you get close to the nucleus in the range of the strong force. So that's a weakness in this model, and it helps explain why electron diffraction, which I'll look at in my next video, is a much better method of directly measuring this. Okay, so those are the assumptions involved. So what we can do is look at how they used the alpha scattering results to actually give an estimation of the size of the nucleus. So a very rudimentary method would be going, well, about 1 in 10,000 was bounced right back, therefore it must be about 1/10,000th of the size of the atom. So that's the first approximation you can make. But an improvement on that is the idea of closest approach. So what you do is you increase the kinetic energy of your alpha particle. And what you're looking for is the kinetic energy you reach when you start getting very odd results from your experiment, which means the strong forces interfered with your experiment. So that's what they did. And once you find that kinetic energy, where you get into the range of the strong force and it distorts your results, then what you can do is say, well, at the closest point, if it's been bounced back completely, so 180 degrees, it must have transferred all of that kinetic energy into electric potential energy, and then that's transferred back into kinetic energy when it rebounds. So what you get is this scenario here, where the kinetic energy is equal to the electric potential energy, and I've been a bit of a muppet and got d squared in there, which is wrong. It should only be d because this is the electric potential energy there. So we get this relationship here, and what we can do is this d will be the distance, was how close it got to it when it got into the range of the strong force. So that will give us an approximation for the size of the nucleus. So that's what they did, and that's where one of the first measured estimates of the size of the nucleus comes from. But it is an estimate, and this is another reason electron diffraction is a better method, because that actually directly measures the size of the nucleus, which is going to give you a better result there. So that's what we'll look at in the next video, electron diffraction, how that it gives us better results there.